Let's investigate polymorphism in Haskell a little more closely. What we have seen is that for functions that only look at the structure of a list, we can make them work on lists of any type. So for instance, the head function takes a list which is non-empty and removes the first element. It doesn't really care what the value of the first element is, it just returns it. So remember, we should think of this in terms of boxes. So supposing we think of a list as a collection of boxes arranged in a row, and somebody asks you for the first box, you can give it to them without opening it. So head, we say, takes a list of any type A and produces a value of type A. Similarly, length just counts the boxes. So it walks down the list, a list of any type A, and counts how many boxes there are and returns an integer. Reverse just rearranges the boxes so that the first is last and the last is first. And finally, take, for example, gives a number. So takes generalizes in a sense head. You say not the first box, I want the first k boxes. So you take a k and then you take a collection of boxes and remove the first k of them. But once again, you don't need to look inside the box. So what about the sorting functions which we saw? We saw insertion sort, merge sort, quick sort. Can we legitimately say that these functions are of type list of A to list of A? Because after all, they take a list and produce a list. And the way that you do, say, insertion sort for integers is the same as for float, and it's the same for many other types that you can think of. So why can't we not say this? So the question is, can we sort any type of list, which is what this type would suggest. It would say that quick sort or insertion sort or merge sort will take any list of A and return back a list of the same type. Now the problem is that lists can contain any uniform type, just as we have seen that we can pass functions to other functions. So there is no specific limitation on what types of objects we can move around between functions. There is also no limitation on what types of objects we can put into a list. So we can as well construct a list of functions. So here is a list of functions. All of them have the type int to int. They take an int as integer as an argument and produce an int as a result. So we have factorial, which is of this type. We have plus 3. Remember, plus 3 is a function which adds 3 to whatever you give it. We have times 5, which will multiply by 5 whatever you give it. So this is a legitimate list. Now, how would I say whether or not the function factorial is less than the function plus 3, or whether plus 3 is greater than or equal to the function multiplied by 5? So what we want to say is that we want to restrict the type of a function like quicksort to all those lists from list A to list A, provided we can compare values of type A. So we want to rule out things like these functions which we don't have a sensible way of comparing. So in Haskell, this is captured using a notion called a type class. So a type class is a collection of types with a required property. In this case, the type class which is relevant to us is the type class called ORD. Notice the capital letter O. Okay, so type classes are usually written with a capital letter, and ORD contains all types whose values can be compared. This includes things like integers and other number types like float. It also includes things like boolean, where false is determined to be defined to be less than true. We have characters which can be ordered depending on their internal representation. So whatever value ORD, the small ORD, the function on characters return. So this allows us to order characters and so on. So capital ORD is a set of all types whose values can be compared. So we can think of capital ORD as a predicate which evaluates to true on a type T if T belongs to ORD. It's not actually a predicate, but let us just think about it this way. So what internally it means is that if T belongs to the class ORD, then the comparison functions less than, equal to, not equal to, etc. are defined for T, which in turn allows us to sort these elements, because these are the values, these are the functions we use to compare values of this type. So now we can write the type of quicksort in this way. It's a kind of conditional polymorphism. So this part says that it is from list of A to list of A, but it's not from any list of A to list of A. It must be a list whose elements can be compared. So there is a new symbol here which you should read as a kind of logical implication. So this says if the underlying type A belongs to ORD, Then quicksort is of a type list of A to list of A. Right? So this is not unconditionally list of A to list of A. This is conditionally list of A to list of A, provided A is an ORD type. So this makes sense for sorting. What about a more basic function we have seen, the function elem, which checks whether a value belongs to a list or not. Okay? So inductively we said that elem of x with an empty list is always false. And if we have a non-empty list, check the first value. If it is equal, then say true. Otherwise, then say false. Or not say false, otherwise check the rest of the list. Right? So here, what we are really doing is checking whether a given value is equal to another value. Now this seems innocuous enough. It would make sense, it seems, to check whether two values are the same or not. Now again, our problem comes because our values include the so-called higher order types, namely functions. So let us look at our old list that we had before, which we had problems sorting. Right? So now the question is, what does it mean to ask whether some other function f belongs to this list or not? We need to be able to check whether f, one function, is equal to g, another function. Is this a reasonable thing to do? So one way, of course, to answer this question is to check whether the value of the function f is the same as the value of the function g for every x. Therefore, in principle, they must be of the same type and they must agree on all the outputs. Okay, so this is sometimes called the extensionality principle. So it would say, for instance, that any correct sorting algorithm is equal to any other correct sorting algorithm, because both of them, when given an input list of the same arrangement, will produce an output list with the same arrangement. So we are ignoring things like efficiency and other characteristics. We are just saying the input-output behavior of the function is the same. So can we not do this? So other than the minor problem that we have to check this for an infinite set of values, there is also the more serious problem that computations don't always terminate. Remember our initial naive declaration of factorial, which ignored the problem of negative inputs. So if we had a function with factorial definition like this, which did not take care of negative inputs carefully, then the value of factorial on something like -1 would degenerate into an infinite computation where it called factorial -2 and then factorial -3 and so on. And therefore this recursive step would never terminate. So we would never get an answer. So even if we could in some systematic way check f of x equal to g of x for all x, at the very least we need to be able to check on the way that f of x is not going to give us a sensible value. So maybe we want to say that whenever, say, f of -1 is not terminating, g of -1 is not terminating. Right? So in particular, we need to be able to check at least this much. Forget about checking the values. We need to at least check that they terminate on the same sets of inputs. So not just that we are weakening our condition. We are not checking that f of x is equal to g of x. We are just asking, does f of x terminate exactly when g of x terminates? So in other words, we need to write a function such as halting, which will take a function, take an input, and tell us, yes, f terminates when evaluated on x. Right? So halting f of x is true provided f of x terminates, false otherwise. So this is the minimum that we need in order to even address the issue of how to compare two functions. And what Alan Turing proved is that this function cannot be computed. Right? So this is his famous result about the halting problem. There is no algorithm which can determine whether another program and an input to that program halts or not. So given that we can't even compute when two functions agree on their terminating inputs, it is clear that we cannot compute any sensible notion of equality over functions. In other words, equal to is not a basic fact for every type in our system. So since equality is not defined on functions, we need to have a type class called EQ, which specifies that a given type has values that can be compared for equality and inequality. So EQ of A holds provided equal to and not equal to are defined on values of that type. So in terms of this type class, we can now give a conditionally polymorphic type for the elem function, which says that provided EQ holds for the input type, then we can take a value of that type and a list of that type and tell whether or not the value occurs in that list. So fortunately, all the built-in types in Haskell, starting with integers, floats, char, bool, etc., all support equality. And if we have a list of values, each of which can compare to equality, we can compare the list for equality element by element. We can compare tuples element by element and so on. So we can extend EQ from the underlying type to structured types. On the other hand, as we have seen, even though we might be able to apply EQ to the input and the output type separately of a function, it doesn't mean that we have EQ defined on the function type, because there is no sensible way to compute equality of functions in general. In the same way, remember that ORD of A holds if the comparison functions are defined on values of that type. Now, if we have a type A on which we can compare values, then we can compare lists of those two values by using lexicographic or dictionary order. Right? So we just list out the values and look for the leftmost value which differs, and based on the order of this leftmost differing value, which is exactly how you look up words in a dictionary, we decide which list is smaller than the other. In the same way, we can also compare tuples, but in the same way, we cannot compare functions. Another type which is very common is the type class num, which tells us whether arithmetic operations are allowed. So remember the function sum, which computed the sum of a list. Right? So the sum of the list just takes 0 as the sum of an empty list and adds up all the values inductively. So sum requires the function plus to be defined on the values of the list. Right? So num of A says that A is a number that supports basic arithmetic operations. So the correct polymorphic type for sum is if num of A, then given a list of A, it produces a value of the same type. Now why of the same type? Well, obviously if you're adding up integers, we'll get an integer. If we're adding up floats, we'll get a float, and so on. Right? So provided the underlying values can be added, we'll get a value of the same type. So num actually has specialized subclasses such as integral, frac, etc. So you can look up some Haskell documentation to see all the various type classes that are built into Haskell. There is a very important class called show, which tells us when a value can be actually displayed to the user. So it requires a function also called show with a small s to be defined. So again, for all the basic types, we have a show function which gives us the representation that we see when we work with GHCI. On the other hand, if we ask Haskell to show what the value of a function is, then obviously there's no sensible way to describe a function, because remember, a function is a black box. It's an input-output box. So we can't possibly describe a function in terms of all its input-output behaviors and display it to the user. At the same time, there may be many different ways of describing a specific computational implementation of a function. So there is no sensible way to assign a function type to the type class show. So what we have seen is that the way that Haskell deals with type classes is to specify them in terms of signatures. It says that, okay, if you want a type to belong to ORD, you must give sensible definitions for less than, equal to, greater than. By sensible, it merely means that you must give a value of the correct type. Okay, it does not introduce any meaning to it. You can give a completely unnatural definition of less than or less than equal to and still claim that something belongs to ORD. It's just that things like sorting will not behave in the expected way. Similarly, any function, any type can be made a member of EQ by providing a suitable definition for equal to and not equal to, and so on. So we will see how to do this later on. We will see how to add our own type classes or to add types to a given type class and so on. So to summarize, a type class is a collection of types that satisfies additional properties over their values. For instance, the ability to check for equality, to compare values by magnitude, and so on. And these additional properties are defined in terms of signatures. Okay, these are additional functions that must be defined on all values of that type in order to use them as part of that type class. And then once we have type classes, we can give conditionally polymorphic types for functions such as sorting, which require the underlying values to have a certain property, or for elem and so on.